Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Bootcamp, Lecture 4. Today we're going to talk about random vectors and independence. Independence is a key ingredient in simplifying statistical models. Independence is a useful assumption, and we frequently use it in statistics to get a handle on complex phenomena. In addition, we'll find that independence and identically distributed random variables are going to be our canonical model for what we might think of as a random sample. So let's just briefly talk about what we're going to cover today. Random vectors, which are simple collections of random variables. Then we'll talk about independence, and you probably have a rough idea of what is meant by independence to begin with, but we're going to talk about the mathematical formalism a little bit. We'll talk about correlation and then go over various mathematical properties of the correlation and covariance operators. And then we'll use our facts about independence and variance and correlation to talk about properties of the sample mean. And then we'll cover the sample variance and end with some discussion. This lecture is actually one of the hardest things in all of statistics. I think if you can kind of understand this lecture, you've understood what the goal of probability modeling and this kind of population modeling really is. You might want to consider listening to it over and over again. And it's incredibly difficult concepts until you internalize them. And then once you internalize them, they seem simple. So what I'm hoping in this lecture to do is to help you internalize them. Okay. So a random vector is nothing other than an ordinary vector with random variables as its entries. So if you have x and y as random variables, then simply the ordered collection x comma y is a random vector. So just like individual random variables have densities and mass functions or distributions that govern their probabilistic behavior, random vectors have joint densities and joint mass functions and joint distribution functions that govern their probabilistic behavior. Let's just simply talk about densities and mass functions to begin with. A joint density f of x comma y, first of all, has to satisfy that it's positive everywhere. It's the two-dimensional random vector. So this surface f exists on the two-dimensional plane, and the fact that f is greater than 0 suggests that its height everywhere is above the horizontal plane. And it has to integrate to 1, but when you integrate over the whole xy plane. So the z direction has to be greater than 0, and the integral over the xy plane has to be 1. So it's a direct extension of the ordinary one-dimensional probability density function. And I think from this definition, you should probably be able to guess what the definition of a joint density is for 5n random variables. And then for discrete random variables, let's say f now is a joint probability mass function, then the joint probability mass function f maps possible values of x and y here, so lowercase x and lowercase y are the possible combined values of x and y, to probabilities. So to satisfy the definition of being a joint probability mass function, f has to be bigger than 0 for all possible combinations of x and y, and then the sum over all possible combinations has to equal 1. By the way, the joint density function exactly works like a univariate density function in that, in this case, volumes under it, so integrals under it, correspond to probabilities. And so the total area is 1. And in the same case with the joint mass function, sums of collections of possible values of x and y yield the probability of that collection. So for this class, a general discussion of random vectors is probably too much. So we're only going to focus on one specific kind of joint densities, the particularly manageable type, and that's when the random variables x and y are independent. And what we'll see is that for, say, a joint density or a joint mass function, if the random variables x and y are independent, then the joint density just factors into the product of the two individual densities, the f of x and g of y. And basically, this is what mathematically independence does for us a lot, is it turns complicated multivariate structures into products. We're going to use this fact a lot, and we'll explain some of the intuition behind this. Thinking back to our early definitions of probability, we were discussing the sample space and events. Two events are independent if the probability of their intersection is equal to the product of their probabilities. So probability of A intersect B is probability of A times the probability of B. So A and B are independent. Incidentally, if this is true, then A is independent of B complement, B is independent of A complement, and A complement is independent of B complement. And the mathematical definition of independence is equivalent to our kind of intuition of what it means to be independent. A is unrelated to B. That's what the mathematical definition implies, and we'll kind of get a better sense of that. For two random variables, we would maybe define that they're independent if you have any two sets, A and B, that probably the X lies in A and Y lies in B is the product of the probability that X lies in A regardless of what Y is doing and the probability that Y lies in B regardless of what X is doing. And so that's just simply a direct extension of the definition of independence above that I think probably everyone is maybe a little bit familiar with. We automatically think of independence all the time already. So if you were to ask nearly anyone who has a basic amount of mathematical training, what's the probability of getting two consecutive heads on two consecutive coin flips, they would probably say, okay, well, the probability of getting a head on the first one is a half, and the probability of getting a head on the second one is half, so it's probably a quarter, right? Well, that is just an exact execution of the independence rule. Let A be the event that you get a head on flip 1, B be the event that you get a head on flip 2. Then basically what you're saying is you want the probability of the intersection, a head on flip 1 and 2. And so then the probability of that intersection is exactly the product of the probabilities via independence. Probability of A times the probability of B. So 0.5 times 0.5, which is 0.25 or a quarter. So we use independence all the time, and the main consequence of independence is that probabilities of independent things multiply to obtain the probability of both occurring. But this creates a problem in that people have then gone on to extend this rule to where they just multiply probabilities regardless of whether they're independent, and this can lead to tragic consequences. Here's a great example. In Science, Volume 309, they report on a physician who gave expert testimony in a criminal trial. And he was giving expert testimony on sudden infant death syndrome, SIDS, which is this tragic phenomenon where a baby dies, for example, in the middle of the night, and no one exactly knows why. So a woman was on trial because she had two consecutive children who died of SIDS. And there was a court case that then considered whether or not this was too unlikely to happen by chance and that there really wasn't SIDS, it was something malicious on the part of the mother. So the person who was testifying did the following calculation. The person said that, well, the probability of SIDS is 1 out of 8,543. I'm not 100% clear where they got that number, but let's assume for the case that's correct. Then the person giving the testimony said, well, then the probability that you have two SIDS would be the product of that number twice, or the square of that number, 1 over 8,543 squared. Based on this evidence, the mother was convicted of murder. So what was this physician's mistake in this case? For the purpose of this class, there's actually quite a bit of discussion you could have over ethics, probability, evidence, and culpability based on this case. There's quite a collection of complicated issues that intersect when you're discussing a case like this. For example, where and how does this probability of a SID come from? What's the evidence for it? How do you balance medical evidence when convicting a person or not convicting a person in a trial? For the purpose of this class, let's just simplify the discussion down to, is this direct calculation warranted of simply multiplying this number twice, given that it's correct? Well, if A1 is the event that the first child died of SIDS and the A2 is the event that the second child did, then the inherent calculation the inherent assumption being made is that A1 is independent of A2, so that you can multiply probability of A1 times the probability A2. But this logic fails immediately. There's no reason to believe that the event of a second SID is independent of the event of a first SID. So in this case, and in many cases in biology, biological processes that have a genetic or familial component would tend to be dependent within families. So you couldn't multiply the marginal probabilities to obtain the intersection. And there's other problems, and I outlined an example of one here with this estimate. The prevalence was obtained from an unpublished report on single cases, and quite a bit of the discussion surrounding this case revolved around these and other issues. But the point I'm trying to make for the purposes of this class is you can't just go around multiplying probabilities willy-nilly. The random variables or events that you're discussing have to actually be independent. Okay, so we'll use the following fact extensively in this class, and we'll use it as a basic simplifying principle. If we have a collection of random variables that are independent, x1 up to xn, then the joint distribution of x1 to xn, or the joint density function, is the product of the individual densities or mass functions. So in other words, the density of f of x1 up to xn is the product of the individual densities. And here I have fi of xi, indicating that every xi could potentially have a different density. The most common model that we'll be dealing with is the instance where x1, x2, all the way up to xn are from the same distribution. And this particular case, we would say that the xi's are independent and identically distributed, the independent being that x1 is independent from x2 and so on, and identically distributed in that f1 is equal to f2 is equal to all the way up to fn. The IID samples are very important in the subject of statistics. And the reason for that is because IID random variables are a basic kind of default model for random samples. If you have a collection of things that are, in essence, we believe exchangeable, then we treat them as if they are IID. And many of the important theories of statistics are founded on the assumption that variables are IID. So to give you an example of IID random samples, imagine just simply rolling a die. Each roll of a die is a draw from the uniform distribution on the numbers of 1 to 6. So when we say that a process, when we model a process as if it's IID, we're saying it's like we're rolling a die for each variable that we're modeling from some population level distribution. I just want to comment on the broader discussion on probability modeling. This is never actually the case, right? It's probably a very good model for rolling a die, but we use IID to model things where surely the variables themselves are not IID. We can rarely guarantee that our sample is actually a random draw from some population distribution F over and over again. The point is that it's a statistical model used to simplify calculations and simplify our discussion. But whenever we use this statistical model, we have to be cognizant of the fact that it is a model and it's an enormously simplifying assumption. Let's just go through a very important example of flipping a coin. So imagine if we have a biased coin, and remember, if we have a biased coin, let's say the probability of a head or a success probability is p, and we flip it n times. Well, what's the joint density of the collection of possible outcomes? Recall, each coin flip here is a Bernoulli random variable with success probability p. And recall, we wrote out the density in the form p to the x, 1 minus p to the 1 minus x. And notice that's a very easy form, right? So if you plug in x equal 1, you get the probability p of a head or of a 1. And if you plug in x equals 0, we get 1 minus p for the probability of a tail or a 0. So this density is a nice way to represent it. And you'll see why we represent it specifically this way in the next line. So the joint density is the joint mass function f of x1 to xn. If they're independent coin flips, right, is simply the product of the individual densities. And you'll see from this formula we get p raised to the summation xi, 1 minus p raised to the n minus summation xi. So if the x's are all zeros and ones, this works out to be p to the number of heads, 1 minus p to the number of tails. And that's basically why we write out the density this way, is because if we have a bunch of independent coin flips, then it's convenient that the mass functions multiply, and we wind up with this nice form for the joint mass function. So if you wanted to say, for example, if I have a biased coin with success probability P, and I had 4 coin flips, and I wanted to know what's the probability of getting a 1 and then a 0 and then a 1 and then another 1, so 1, 0, 1, 1, you would just simply plug into this formula. And notice the order of 1, 0, there we got 3 heads and 1 tail. Notice the order doesn't matter. We would need P to the 3, 1 minus P to the 1 would be the probability of that occurrence. And notice it's the same probability regardless of what order the 1s and 0s occurred. So this formula makes it easy to calculate the joint probability for a collection of 1s and 0s from a potentially biased coin flip. I just want to mention again that this model is tremendously important. So imagine, for example, we want to model the prevalence of hypertension in a population. One way we might go about doing that is to say that our sample is IID. And again, that's often a big assumption that people are IID draws, individuals are coin flips, and what we would like to know is their success probability of having hypertension. And so that success probability is the prevalence of hypertension in the population, and we would use this joint mass function to model that process for our collection of data. And that's the idea behind where we're going with this. But notice there's a lot of assumptions that go into that, right? I just want to emphasize this fact quite a bit. We're assuming that we're randomly drawing people from the population that we're interested in, or not even that we're randomly drawing them, but that we can model the collection of people, their hypertension status, as if they were a bunch of independent coin flips with the prevalence being the success probability. That's ultimately what our model is stating. So it's important to always keep that in mind. So let's stop here, and we'll next talk about some of the mathematical properties associated with random variables and covariance and correlation and their consequences when variables are independent. Okay, so welcome back, troops. We're going to talk about covariance and correlation now, and what happens when random variables are independent. So if we have 2 random variables, x and y, then their covariance is defined as, here, cov x comma y, the expected value of x minus its mean times y minus its mean whole quantity. And just like the variance, there's a shortcut formula for covariances. And it works out to be expected value of x times y minus the expected value of x times the expected value of y. So there's some very useful facts about covariance. First of all, the covariance, you can interchange the variables and you get the same number. So covariance of x comma y is covariance of y comma x. The covariance can be negative or positive, but in an application of so-called Jensen's inequality, we'll tell you that the absolute value of the covariance of x comma y is less than or equal to the square root of the variance of x times the variance of y. So we could just write this right-hand side as the standard deviation of x times the standard deviation of y. This final property is very useful because, as we go on to the next slide, we use it to define the correlation. The correlation of x and y is nothing other than the covariance divided by the product of the standard deviations. So there's a couple reasons why we might want to do this. From the previous slide, notice that this then normalizes the covariance so that it's between -1 and +1. And that's a very useful thing to do so that maybe we can somehow utilize the idea of covariance across different kinds of random variables. Now, another rationale for doing this is if we look back at our covariance formula, right, it's expected value of x minus the mean of x times y minus the mean of y. Well, that has units of x times units of y, right? So the top part of the calculation has units x times units y. The standard deviation of x has units of x, and standard deviation of y has units y. So the bottom part has units x times units y. So the correlation is a unit-free measurement. That's a useful property to have. So if x is in inches and y is in pounds, then the covariance is in inches times pounds, but then the correlation is then unit-free, which is useful. Correlations have some nice properties. One is that the correlation is only plus or minus 1 if and only if the random variables are linear related, x equals a plus by for some constants a and b. Correlation is unitless, as we discussed already. And then we say x and y are uncorrelated if correlation x and y are 0. And sort of the more positively correlated they are, the closer correlation, core x comma y gets to 1, and they're more negatively correlated as core xy goes to minus 1. And this is, again, a description of a population quantity, not a sample quantity, right? So this is a description of you're using a joint probability mass function or joint probability density function to model the population behavior of x and y. Then we want ways to summarize that joint mass function or joint density function. And the correlation is a summary of how related joint random variables are from this distribution. So it's a summary of a population quantity. And of course, if something's a population quantity, we want sample quantities that are able to estimate them. So probably what you've heard of if you've never had a mathematical statistics class before is the sample correlation. And again, the goal of the sample correlation is to estimate the population correlation if you're using a probability model. So the sample correlation estimates the population correlation. So if you've ever had a sample correlation and you've had a probability model, what you are trying to estimate is the population correlation. The estimand is the population correlation. So it follows the same rule we have so far for everything. The sample variance estimates the population variance. The sample standard deviation estimates the population standard deviation. The sample median estimates the population median. So all these sample quantities have analogous population quantities. So if two random variables x and y are independent, then their correlation is 0. The reverse is not true. Things can be uncorrelated but not be independent. So if they're independent, then they are uncorrelated, but if they're uncorrelated, they're not necessarily independent. In the case of Gaussian random variables, by the way, the two things agree always. But in general, that's not always the case. So let's talk about some useful results that rely on correlation and covariances. And probably the most useful one we'll talk about is this variance idea. So if we have a collection of random variables, x1 to xn, when the x's are uncorrelated, and here I wrote out a very general form, the sum of the x's may be times some constants ai plus a constant b, works out to be the sum of ai squared times the variance of the individual x's. And let's think about the specific case when b is 0 and the a's are all 1. That just means that the variance of the sum is the sum of the variances. And here we just wrote out a slightly more general term. We know in general that constants pull out of variances and get squared. That's why you have the ai squared. And we also know that if you have a random variable and you shift it by a constant b, it doesn't change its variance. It just moves the density to the left or right. So it doesn't change the variance. So the a's and the b's are kind of fluff on top of this equation. The core of this equation is just think about the instance when b is 0 and a is 1, that when the x's are uncorrelated, they don't have to be independent. They just have to be uncorrelated for this result to hold. Then the variance of the sum is the sum of the variances. If they're not uncorrelated, then you can actually calculate what their variance is in a way that it depends on the covariance. It works out to be the sum of the variances with the ai squareds out front plus twice the sort of sum of all the pairs of covariances. So this is a very useful formula. We won't use it in this class, but I thought I'd give it to you. And so notice if they're all uncorrelated, all these terms here are 0, and then we get the top formula. The top formula is what we're really going to use in this class. And it basically says that the variance of the sum is the sum of the variances if you have independent events. The other important thing that this kind of says is that you shouldn't be adding standard deviations. You should probably be adding variances, is another way to kind of think about it in general. So this leads to an interesting proof of a useful property that the variance of x bar, the sample mean, is sigma squared over n. And it also leads to the fact that the expected value of the sample variance is sigma squared. These are two very important properties that we'll go on and on about. Okay, so I don't want to prove the general facts from the previous slide. Let's just go through the heuristic because it's pretty easy to do. So let's prove that the variance of x plus y is the variance of x plus the variance of y plus twice the covariance of x and y. So at the top line, let's start with variance of x plus y. Well, just by the definition of variance, right, that's the expected value of x plus y squared minus expected value of x plus y quantity squared, right? So if you're confused by that, just replace x plus y with a random variable z, and it's expected value of z squared minus expected value of z quantity squared, directly plugging into the shortcut variance calculation formula. Well, the right-hand element here is expected values always commute across sums, so we have mu of x plus mu of y quantity squared. And the left-hand side, let's just expand out this x plus y squared to get x squared plus 2xy plus y squared. And then let's just move the expected value across the three elements of this expression. Well, then let's just organize terms, and we get expected value of x squared minus mu of x squared plus expected value of y squared minus mu of y squared, and then 2 expected value of xy minus mu x mu y. Well, this first one, expected value of x squared minus mu x squared, that's variance of x. The second one, expected value of y squared minus mu y squared, that's variance of y. And this latter part, 2 expected value of xy minus mu x mu y, right? Expected value of x times expected value of y for this right-hand part. Well, that's just covariance of x comma y, completing the proof. So you can see that it only requires the basic rules for expected values to perform this calculation and the definition of covariance to perform this calculation. So just to reiterate some things we discussed earlier, if a collection of random variables are uncorrelated, then the sum of the variances is the variances of the sum. So what it basically means is that sums of variances tend to be useful, not sums of standard deviations. And this is just the issue I'm trying to raise is don't sum standard deviations. So in other words, the standard deviation of the sum of a bunch of independent random variables is the square root of the sum of the variances, not the sum of the standard deviation. So it's just a common little problem, so maybe trying to avoid it from the start. There's an important result that arises out of these facts. And the important result is that the variance of the sample mean of a collection of independent and identically distributed random variables is sigma squared over n. So let's assume that we have a collection xi, I equals 1 to n, that are independent and identically distributed, IID, and that the variance of the distribution that they're drawn from is sigma squared. Okay? So let's calculate variance of x bar. Well, that's just the variance of 1 over n times the sum of the x's, right? That's just the sample mean formula, the sum of everything divided by the number of things you added up. The 1 over n is a constant, so we can pull it out, 1 over n squared, and we get the variance of the sum. The variance of the sum is the sum of the variances because the x's are independent, hence uncorrelated. And then because they're IID, the variance of each xi is the same. It's sigma squared, and we've added up n sigma squared, so we get n sigma squared. And so it works out to be sigma squared over n for the final line here. So what does this mean? It's really quite an interesting fact. What this says is if I want to know what's the variance of the distribution of averages of 10 random variables, say, from a distribution, I don't actually have to know what that distribution of averages actually is. So I don't have to do that. All I have to know is what the variance from the original distribution that the individual observations are drawn from, and that gives it to me. I just have to divide that by n, right? So if I want the variance, I divide by n. If I want the standard deviation, take the original standard deviation and divide by square root n. And why is this important? Because remember, eventually we'd like to connect all of these ideas, these population model ideas, to data. And if we have a bunch of things that we're willing to model as if they were IID, well, we get multiple draws from the distribution of individual observations. All the xi's are separate draws from the original distribution. So we can estimate things like sigma squared, but we only get one sample mean. Let's say we have a sample of 100 observations. We only get one sample of 100. So if we calculate the sample mean of all those 100 observations, we have nothing empirically to estimate the variance of sample means of 100 variables. We don't have repeated samples of 100 variables. We only have the one. Well, what this result says is you don't need that, right? Because all you need is the variance of the original population and divide it by n. The variance of the original population is something we can estimate. And so it's a very nifty result. Let me give you an example of this property that you could do at home to just test this result to make sure it's true. Recall in the last lecture, we said the variance of a die roll, which takes values 1 to 6 with equal likelihood, 1/6 for each number. The variance of a die roll was 2.92. Okay? So what that says is if you roll a die over and over and over and look at the distribution, you'll get about 1/6 of each number. And that the variance of that distribution, so if you were to roll it thousands and thousands of times and take the variance of the thousands of measurements, you would get around 2.92. So do that. Roll a die a lot of times and take the sample variance of 1,000 die rolls, for example, and you'll get about 2.92. Why is that? That's saying because the sample variance of lots of die rolls estimates the distribution of the population of die rolls, which is this uniform distribution on 1 to 6, and its variance is 2.92, so you'll get that. Now here's the question that the calculation on the slide is answering. Suppose now, instead of rolling a die over and over again, you rolled 10 dice and took their average and repeated that process over and over again. Right? So now this would no longer be uniform on the numbers 1 to 6. Still, the minimum would be 1, right? If you got all 10 ones, the average of 10 ones is 1. And the maximum would still be 6. The average of 10 sixes is still 6. And so the bounds are 1 and 6, but it would not look like a uniform distribution on the numbers between 1 and 6, because you can get all sorts of different numbers, right? You can get numbers between 1 and 2, 2 and 3, and so on. So it has kind of a funny distribution, the distribution of averages of 10 die rolls. So imagine if you were to do that, roll your 10 dice and take the average and do that over and over again so that you got, say, 10,000 averages of 10 die rolls, right? And you wanted to know what was the variance of that distribution. Well, it seems kind of like a hard calculation. First, you'd have to figure out what's the distribution of the average of 10 die rolls, which seems kind of like a hard distribution. And we'll actually later on discuss that that's maybe even a little bit easier to calculate than you might have thought. But this calculation says you don't even have to worry about that. We know that the variance of the distribution of individual die rolls is 2.92. So the variance of the distribution of averages of 10 die rolls is 2.92 divided by 10. So it would be 0.292. And so we could run this experiment in R, for example, where we rolled a digital die thousands of times and took the variance of 1,000 die rolls, and you'd find that's about 2.92. And then we could also do this experiment where we rolled 10 dice, took the average, and repeated that process over and over again and got 10,000 averages of 10 die rolls. And you would find that the variance of those averages was about 0.292. Very interesting. And so it's a very simple formula. And so let's belabor this point on the next slide. So when the x's are independent with a common variance, the variance of x bar is sigma squared over n. The quantity sigma over n, the square root of this, is so important, we give it a name and we call it the standard error of the sample mean. Basically, a standard error is nothing other than the standard deviation of a statistic. In this case, the statistic is the sample mean, but you might have a standard error of another statistic. For example, the median then itself has a standard error. It's maybe a little hard to calculate, but nonetheless, it has a standard error. So what is the standard error? The standard error of a sample mean is the standard deviation of the distribution of the sample mean. So sigma, the standard deviation, talks about how variable the population is. Sigma over square root n talks about how variable the population of averages of size n from that population are. So two different statements, and they estimate different things. So for example, if the x's are IQ measurements, sigma talks about how variable IQs are. Sigma over square root 10, say, then talks about how variable averages of 10 IQs are. Okay, so they're different. They're obviously related, but they're different concepts. And it's easy to confuse the two. And an easy way to remember this, by the way, is that the sample mean has to be less variable than a single observation. Therefore, its standard deviation is divided by square root n. So that also gives you a sense of how the rate at which standard deviations decline as you collect more data. So since we've talked about the sample variance a lot, why don't we actually define it? So the sample variance is that entity that we use data to estimate the population variance. So recall the population variance was the expected value or the average, the expected deviation of a random variable around its population mean, right? So what is the sample variance? Well, it's the average deviation of the sample values around the sample mean. So it's quite convenient. Now notice it's not exactly the average. We divide by n minus 1 instead of n, which is a little annoying, but we do it. So imagine for the time being that this is an n in the denominator, not an n minus 1. Then the sample variance is nothing other than the average squared deviation of the observations around the sample mean. So the sample variance is an estimator of the population variance, sigma squared. And just like the population variance has a shortcut formula, the sample variance has a shortcut formula. Summation xi minus x bar squared, the top of the variance calculation, is summation xi squared minus nx bar squared. So if someone gives you the sum of the squared observations in the sample mean, then you can calculate the sample variance really quickly. So why do we divide by n minus 1 instead of n? And again, for large samples, it's irrelevant, right? The factor n minus 1 over n is small, so you're going to get about the same answer either way. But for small samples, it can make a difference. So why do we choose to divide by n minus 1? So recall we have this property, unbiasedness. And the property of unbiasedness meant that the statistic, its expected value, equaled the quantity that it's estimating. So just to remind you, the sample variance is a function of our observed data. It's a function of our random variables, right? So itself is a statistic. So it is a random variable itself. So it has a distribution. And so that distribution has a variance and that distribution has a mean, okay? That's what we're going to talk about right now, is that the mean of that distribution turns out to be sigma squared if you happen to do the calculation where you divide by n minus 1. So I'm going to show it by showing that the expected value of the numerator of this statistic is equal to n minus 1 times sigma squared. That's the same thing as showing that the sample variance is unbiased, because then you just divide both sides of this equation by n minus 1 and you get the result. So let's do that. Just to say it again because it's important, what are we doing? Remember, the sample variance is itself a random variable. That random variable has a distribution. That distribution has a population mean. And we want to say that that population mean is in fact sigma squared. Okay. So expect a value of the numerator part of the sample variance calculation, the sum of the squared deviations around the sample mean. If we use the shortcut formula, that's sum of the expected value of the xi squared minus expected value of x bar squared. Okay. And now let's use a really kind of nifty fact. Recall for the variance, the shortcut variance formula was defined as the expected value of a random variable squared minus the expected value of the random variable quantity squared. Well, we can shift that formula around to get it to say that the expected value of a random variable squared is the variance plus the mean squared. And that's what we do right here. So the expected value of xi squared is variance xi plus mu squared. Okay? And then the same thing is true, of course, for the mean, because the mean itself is just another random variable. So the expected value of x bar squared is variance x bar plus mu squared. And then we have this n out front. Okay. And so the variance of xi is sigma squared. So we wind up with some sigma squared plus mu squared, which is a constant. So we wind up with n of those. And then variance of x bar, we just derived a little bit ago as being sigma squared over n. So we get n times sigma squared over n plus mu squared. And just collect terms now and you get n minus 1 sigma squared. So this is a really interesting fact. So this says that the expected value of the variance is in fact the quantity it's trying to estimate if in fact you divide by n minus 1 instead of n, and that's why we divide by n minus 1. Another way to kind of think about this is that, well, we don't know the population mean, mu, and if we knew it, instead of plugging x bar into the sample variance formula, we would plug mu into the sample variance. We would calculate the deviations of the observed observations around the population mean rather than the deviations around the sample mean. And so the idea is that we will sort of lose a degree of freedom by plugging x bar, its sample analog, instead of plugging in that mu. So that's the kind of heuristic behind why you divide by n minus 1. It's an interesting fact, though. It's not 100% clear that you do want to divide by n minus 1. It's sort of every introductory statistics textbook divides by n minus 1. But there's this interesting phenomenon called the bias-variance trade-off. And in this case, we've obtained an unbiased estimator by dividing by n minus 1 instead of n. But what if we had divided by n? Maybe as an exercise, I could ask you to calculate the expected value of the sample variance if it was calculated with n in the denominator instead of n minus 1. Okay, so basically, what's the expected value of n minus 1 over n times s squared? And you can calculate that very easily. It's not sigma squared, but it's quite close to it. So it's a biased estimator, but the other thing I would ask is, well, which of the two estimators, the estimator s squared calculated with n minus 1 in the denominator, or the calculation of the variance with an n in the denominator, has a lower variance? And what do I mean by that? Remember, the sample variance is a random variable. It has a distribution. That distribution has a variance. And the question is, which of the two calculations, dividing by n or dividing by n minus 1, results in a smaller variance of that distribution? And what does that mean? That would mean how precise your estimate of the variance is. I'll give you the punchline. The sample variance divided by n has a slightly lower variance than the sample variance divided by n minus 1. So it's another kind of classic bias-variance trade-off. In this case, we divide by n minus 1 because we want unbiasedness, but then we wind up with slightly greater variance. If we divide by n, we wind up with a slightly lower variance of our sample variance, but it's slightly biased. I know extremely well-established statisticians that say they would prefer to have the lower variance, but pretty much every introductory statistics textbook divides by n minus 1. It's kind of an interesting discussion. One of the confusions that always comes up seems quite simple. We divide by an n minus 1 when we calculate the sample variance. People have a tendency to confuse that with the n that we divided by when we talked about the standard error of the mean. And so let's just try to avoid some of this confusion. Suppose you have a bunch of observations that you're willing to model as IID with population mean mu and population variance sigma squared. Then the sample variance s squared estimates the population variance sigma squared. The calculation of s squared involves dividing by n minus 1, and we just spent forever talking about the difference between dividing by n and dividing by n minus 1. Then the standard error of the mean is sigma over square root n. So s over square root n will estimate the standard error of the mean. So we've already divided s squared by n minus 1, then we square root it, and then we divide by an additional square root of n if we want the standard error of the mean. Okay, and I'm just trying to avoid some confusion because people seem to get confused by that. So I guess if you wanted to attach a label to the quantity s over square root n, it's the sample standard error of the mean. What does it estimate? It estimates the population standard error of the mean, sigma over square root n. Let's tie this down with some actual numbers. So I was involved in a study where there was a lot of organo-lead workers. In this case, I took a subset of 495 of them. And the total brain volume for the lead workers, they were interested in studying how their exposure to lead in their job changed their brain volume. So TBV stands for total brain volume. in this case is a measure of the brain volume on the inside of the skull. So all the measures are in cubic centimeters. So the mean in this case is 1,151. If we're willing to assume these organo-lead workers are, say, an IID draw of organo-lead workers from a population that we're interested in, then the sample mean 1,151 would be an estimate of that population mean. The sum of the squared observations works out to be this number. So the standard deviation, the sample standard deviation, works out to be that number minus 495 times the sample mean squared, all divided by 494, that minus 1 in the denominator. Square root the whole thing, you wind up with 112. So what does 112 describe? 112 describes the variance of the population of brain volumes of organo-lead workers. Okay, so it's a direct estimate of my sample variation, right? And then it's an attempt to estimate, if you view my data as a sample from a population of organo-lead workers, it attempts to then estimate the population standard deviation of that distribution. So we could, for example, use Chebyshev's rule to interpret what the combination of the mean and the standard deviation say about brain volumes of lead workers in the population. Now, what does, if I take this 112.6 and divide it by square root 495 give me? It gives me 5 as the numerical result. But what does that 5 actually estimate or do for us? Well, the 5 is no longer talking about the variation in total brain volumes in the population. It's talking about the variation in averages of 495 organo-lead workers. So the idea is, if we're willing to model our 495 organo-lead workers as a draw from a population of organo-lead workers, then 5 estimates the distribution of averages of 495 draws of organo-lead workers from that population. It talks about how variable averages of 495 brain volumes are. The 112 talks about how variable brain volumes are. Okay, so let me just repeat that because it's very important. The 112 talks about how variable brain volumes are of organo-lead workers in the population, and it directly talks about it in the sample, but it's an estimate of our population variance. And the 5 is an estimate of the population standard deviation of averages of 495 organo-lead workers. So I hope you're getting a sense of what these numbers are trying to calculate. So there's several concepts that are being used here. First, we have our observed data, right? And these quantities, the sample mean, sample standard deviation, and standard error, tell us things about our observed data, right? And then there's the assumptions, for example, that they're IID, that help to try and connect it to a population so that we can maybe generalize the results from this data to a population of organo-lead workers. Say, for example, if you wanted to use this data to inform policy, and then these numbers would then be estimates of these population quantities, and then dividing by the square root 495 is telling us things about how variable this mean is relative to the variability in the population. Okay, so that's the concepts we're trying to use, and we'll formalize these much more when we actually do things like generate confidence intervals and perform hypothesis tests and these things.